Hi, and a very good day to everyone. My presentation today entitled Lyotropic Liquid Crystalline Nanoparticle for Better Encapsulation and Release of Poorly Soluble Aripiprazole Drug. We move on to the first slide. So these lyotropic liquid crystalline nanoparticles have often been developed when these amphiphilic lipids are subjected to this aqueous environment. So there are several advantages for this reverse type lyotropic liquid crystalline nanoparticle, which involve odate and versatile nanoparticles. They have large internal surface area for the drug. They have biodegradable and biocompatible properties in our body. They have higher bioavailability for the drug that we consume, in which in return it can help to improve the drug pharmacokinetic and it can ease the uptake of the macrophage because of the smaller size of the nanoparticle. Firstly, let's take a look at the encapsulation efficiency finding. So as this aripiprazole concentration increased from 1 mg per ml to 5 mg per ml, the encapsulation efficiency of aripiprazole into the nanocarrier were above 92% in all of this formulation. This indicates drug had been successfully encapsulated into the lyotropic liquid crystalline nanoparticle. However, the higher aripiprazole concentration of 5 mg per ml showed absence of the increment in the encapsulation efficiency. So, this indicates maximum encapsulation efficiency of the drug into the nanocarrier was below than 93%. Secondly, I'd like to take a look at the encapsulation efficiency stability test over 5 days period. So this result showed decreased amount of encapsulated drug in which it accompanied with total reduction of 3.74, 1.55, 1.52, and 1.02 respectively. Overall, 1 mg per ml of the loaded lyotropic liquid crystalline nanoparticle was relatively unstable as compared to the another 3 nanodispersion. This trend demonstrated that as aripiprazole concentration increased, the stability of the encapsulation efficiency increased as well. So this caused the drug to diffuse in slower rate from the citrum SPC bilayer to the outer aqueous phosphate buffered saline, PBS. As you can see in this diagram of the dynamic light scattering analysis, it could be observed that the increase in both of the particle size, this one, and the polydispersity index had been resulted with decrease in the zeta potential from both of the drug-free and the drug-loaded allotropic liquid crystalline nanoparticle. So, this increment might be due to the occurrence of the collision between the allotropic liquid crystalline nanoparticle causes them to aggregate and become bigger particle because of the insufficiency of the steric stabilization to keep it together. This was supported by the zeta potential from each of the formulation, which had been resulted with minimum zeta potential of less than plus minus 30 MV. This indicates weak electrostatic stabilization of this nanocarrier. Moving on to the structural characterization. So, as you can see here, mainly the principle involved with the X-ray which had been sent through onto the nanostructured sample, fall onto the detector and produce a scattering pattern full of the nanostructure informations. So this is the result that we've obtained for 4 of the formulation, which had been resulted with reverse hexagonal accompanied with increasing aripiprazole concentrations. Taking small angle X-ray scattering result before into consideration, transmission electron microscopy analysis also reveal a non-lamellar nanostructures for both of the drug-free and drug-loaded lyotropic liquid crystalline nanoparticle. However, the drug-loaded lyotropic liquid crystalline nanoparticle demonstrated highly odate pack because of the stronger interaction between aripiprazole drug with the citrum SPC bilayer. Let's now have a look at the drug release profile from 2.5 mg per ml of the aripiprazole loaded lyotropic liquid crystalline nanoparticle, which discovered sustained release performance. This might be due to the drug-enriched core model, encapsulated by the outer lipid shell of nearly drug-free. I'd like to draw your attention to the FTIR analysis, so involving this drug and nanocarrier interaction. Referring to the FTIR spectrum of the aripiprazole here, it can be concluded that the characteristic peak of the aripiprazole were present. Now, take a look at the second spectrum of the drug-free nanocarrier. It can be seen that the characteristic peak of the glycerol, citric acid, carboxylic acid, and ester were present. This brings us to the last spectrum of the aripiprazole-loaded lyotropic liquid crystalline nanoparticle, in which it can be concluded here that there are molecular interaction between aripiprazole drug and nanocarrier. Next, I would like to move on to the physical and chemical changes of the lyotropic liquid crystalline nanoparticle. So, considering the DSA thermogram of the SPC with three-phase transition, the first phase occurred at 96.59, in which it indicates transition from ordered gel phase to less ordered crystalline phase. Next transition at 190.43. This indicates transition from crystalline phase 1 to crystalline phase 2. The transition of 262.81 indicate transition from the crystalline phase 2 to less ordered lamella bilayer. Now, take a look at the DSA thermogram of the citrum, in which this indicates two transition temperature. The first transition at 112.98 indicate transition from dull phase to less ordered lamella phase. So this might be due to the progressively weakening of the citrum head group interaction. The second transition at 230.40 from less ordered molecule to freely moved citrum molecule. Next, I want to draw your attention to the DSC thermogram of the aripiprazole, which demonstrated three transition temperature. First phase occurred at 88.51, indicate dehydration process of aripiprazole. The second transition at 139.76 indicate melting point of aripiprazole crystalline phase 2. The third transition at 148.57 demonstrated melting point of aripiprazole crystalline phase 1. So next, I'd like to point out interesting analysis on the DSC thermogram of the drug-free lyotropic liquid crystalline nanoparticle involving the phase transition temperature at 110.53 degrees Celsius, in which this shift of the transition of SPC from 96.59 to 110.53, which is the current peak that had been took place, indicate van der Waals interaction. The van der Waals interaction took place between the citrum and SPC. So the broadening peak that you can see here is caused by the particle size distribution of the nanoparticle. The absence of the SPC peak at 262.81 before was due to the stronger interaction of citrum SPC bilayer. This brings us to the last DSC thermogram of the drug-loaded nanocarrier involving the phase transition temperature at 180.80 degrees Celsius. So, as you can see here, the shift of the transition from 110.53 to 108.8 indicate interaction between the aripiprazole drug with the citrum and SPC, causing the SPC lipid bilayer in the aripiprazole loaded nanocarrier to be more closely packed than the drug-free lyotropic liquid crystalline nanoparticle before. So this result is in good agreement with current TEM analysis that had been presented in the previous slide. As conclusion, this study suggests the potential use of the lyotropic liquid crystalline nanoparticle as a promising nanocarrier for aripiprazole delivery to improve the pharmacokinetic and strengthen the stability of the lyotropic liquid crystalline nanoparticle in the body system. This is the references part. I think that's all from me. Thank you for listening.